and I will start with the pinch flow fractionation, which also is quite easy to understand because we can explain it with the stuff we learned in the fluid dynamics lecture. And for this, I want you to take a look at this picture. So you have a buffer stream, which is some kind of liquid, and then you have a particle stream. And here you have different particles, large particles and small particles. And then you have this pinched segment, and as you can see, the smaller particles can come closer to the wall compared to the large ones, because so you can think of that the mass point is closer to the wall for the small particles compared to the big particles, and this means that they enter different streamlines. And if you remember our fluid dynamics lecture, we spoke about those, so if you have a channel, we spoke about those different, the concept of those different lamellae, if you remember, and those, so like different layers of fluid, and they do not interact but they slide along each other, okay? And so the smaller particles end up in those lamellae, so on the streamlines which are closer to the wall, so they have a lower velocity. And the bigger particles would, for example, end up here. And now, if you look again at this image, you can see that the particles, because the whole flow is laminar, follow their lamellae, and so they end up on different lines in the bigger channel. So the smaller particles are transported more radially outward here, and the larger particles are more in the middle. So it's based on the concept that those particles enter the different streamlines or lamellae and stick with them. So it's purely a hydrodynamic effect that leads to the separation of particles of different sizes in such a system. The next concept is actually quite straightforward. It's the particle trapping concept. And here you have, for example, a channel which looks like this. So you have a large channel which goes in this meandering pattern, and then you have small traps which are also connected here. And when the first particle enters, it will be stuck in this position, and all the other particles will then use this bypass. Then the next particle will be trapped in this position, the other ones use the bypass, and so on. So this is also basic hydrodynamics. Actually, all particles just want to go straight, but if the path is blocked, they cannot, and also the hydrodynamic resistance increases. So the liquid and containing the particles will take the bypass. And using this concept, you can quite efficiently trap particles, which could be either beads or, for example, single cells or something. So those are two examples. There are, of course, many different ones. You can use all kinds of principles, but it would be way beyond the scope of this lecture to present them all. This is just to give you an idea what kind of solutions there are. Alright, so the next topic we are talking about is the microfluidic large-scale integration. So we covered the physical basics, we covered some unit operations, and now we want to discuss quickly what can you do with it. And this is maybe the most famous example what you can do with pump-driven microfluidics. And we start by very briefly discussing how you can let's say fabricate the chips we're discussing in a couple of seconds. And I just want to give you an idea. So this large scale integration is usually done in PDMS technology, and this is an elastomer that is quite often used in microfluidics. We also use it in our lab. And this is done because chips can be quite easily fabricated, so you can cast PDMS, you can demold it, and so on. And the basic process is that you, with some process microstructure, a master. This can be done by milling or by soft lithography like imaged here. So you have some kind of master, and then you cast your PDMS on this master, and once that PDMS became solid, you can just demold it, and then you have microfluidic structures. And while in this example on the image here you just have some pins in your PDMS or like chambers, you could also imprint a whole microfluidic network. So this is how basically you can create those PDMS sheets that can be used for microfluidic chips. And the PDMS technology for those microfluidic large-scale integration was, I think, I don't know if it was introduced, but at least the Quake group from Stanford is maybe the most famous group who used it to develop highly complex pressure-driven chips. And the technology is today commercialized by Fujitsu, and we are going to see the chips right here. So this chip here, you can see on the lower part, is one of the Fujitsu chips. And basically what is interesting is that you can see the size compared to the hand, so it's roughly the size of a microtiter plate. And the microfluidic chip is basically this part here in the middle, which is illustrated here. And the rest is mainly for reagent loading and external connections and stuff like that. And what you can see already here is the fact that it looks highly complicated. You have a lot of connections to the external world, but you have this high integration density. So you can perform all kinds of operations here. And it looks a little bit like those integrated circuit technology. And what I want to discuss with you within the next minutes is how is it possible to design such a system, and what needed to be, or what is the basis for this kind of complex layout.